Hello, SPH3U. It's Mr. LaRusso. Today's note, we're going to be talking about the properties of sound, which is just an extension of the wave theory. So let's talk about what sound is. So sound is a mechanical wave, and specifically in most of our experiences, sound occurs in the atmosphere through air, but sound also travels through other media as well, including water, solids. This is why you can hear sounds in buildings coming through the walls and whatnot. Sound through air and water is a form of a longitudinal wave where we have compressions, rarefactions, and compressions. However, representing a sound wave as a longitudinal wave for analytical purposes is really challenging. So generally speaking, most devices convert the sound wave visually into a transverse wave. So it's easier to draw on an oscilloscope, for example. But it is technically a longitudinal wave, but we represent them as transverse waves. So the trough represents the rarefaction, the crest represents the compression. Of course, these are the equilibrium points where the medium itself is not compressed or experiencing rarefaction. Now, let's talk about the speed of sound. Now, the speed of sound, specifically here, we're talking about the speed of sound in air. Now, sound has some interesting properties, and the speed of sound for most frequencies is a constant, except for when you get into extreme states like thunder, which are not technically sound waves, they're shock waves. And with shock waves, you get a weird sort of effect. That's why when you hear distant thunder, you get the crack happening first, then the boom, then the rumble. That property is something called dispersion. And if you've ever been close to a lightning strike, the explosion sound is one big bang that happens all at once. But the greater the distance you travel, you get this weird effect where the frequencies split apart. The high frequencies travel a little faster than the mid-range, which travel faster than the low frequencies. But generally speaking, what we've got here is a consistent formula for most frequencies, and that's this. So the speed of sound is equal to 332 plus 0.6 times the temperature in Celsius. So let's do a quick example here. Let's say the air temperature is 25 degrees Celsius. All right, well, in that case, what is the speed of sound? Well, the speed of sound is equal to 332 plus 0.6 times the temperature, which is 332, plus 0.6 times 25. That's 347 meters per second. Now, here's the interesting thing. That's about the typical sort of temperature we get in the summertime. You know, it varies between, high teens to low 30s. So on average, it's around 25 degrees Celsius. And that's generally with thunderstorm season. So during thunderstorms, you may have remembered as a little kid, if you were ever afraid of a thunderstorm, maybe your parents or somebody told you that all you have to do is count the amount of time it takes between the flash of lightning and the flash of the thunder, and you can determine how far it is away. Now, that when I was taught as a little kid, I was always told the following thing: 1 second equaled 1 mile. Now, it's funny that miles was used, but that's because when I was a kid, it was the 1970s, and Canada, we were still using miles as opposed to kilometers. It didn't switch over till about 1979, I think. So 1 second equals 1 mile. All right, so the idea was this: you would see the flash of lightning, and then there would be some delay, and then of course you'd hear the roar of the thunder. So the idea was, if you would count the amount of time between the flash of the lightning and the boom of the thunder, you could tell how far that is. And that is conceptually correct. However, this is incorrect. And as it turns out, 1 second does not equal 1 mile. Equally as incorrect is the updated version that 1 second equals 1 kilometer. That is also trash. No, as it turns out, that the speed of sound is roughly a third of a kilometer. 347 meters per second, that's roughly around a third of a kilometer. And remember, this is just an approximation. So therefore, the actual value is closer to 3 seconds equals 1 kilometer. And I wrote 1 meter. Amazing. Kilometer. There we go. All right. So let's put that into practice here. So thanks to good old YouTube, we have a pretty cool video of a shock wave from an explosion. I want you to focus down here, and hopefully you'll be able to hear the sound of the explosion, but you'll be able to see the shock wave. So now you can see the shock wave moving across.
Oh man!
and then you heard the blast. All right, so let's rewind that. So let's look at the time and find out when the explosion first happens. So we're continuing to take a look, and I think it's around 11 seconds. And of course, I accidentally fast forwarded it instead of pausing it because, or rewinding, I should say. All right, so let's take a look. 11-second mark. Okay, so around the 11-second mark, and take a look here. You can really see the shock wave. So let's get a little highlight here going on. So you can see that shock wave starting to move. All right, it's pretty intense. And there it is right there. You can see it again. Get the pen. So you can see the wavefront of the shock wave right there. So this is an extreme compression. Now, if you're in this region here, RIP your ears. The shock wave would blow out your eardrums, and that would result in permanent deafness. Now, the other thing is the shock wave will probably not only just blow out your ears, but the shock waves would probably commit such intense internal damage to your organs that you would likely die of your injuries before even the flame got to you. And most people die as a result of the initial concussion of the shock wave that does internal damage. That's how much pressure there is, as opposed to the actual fiery death of the explosion itself. Fortunately, the individuals that filmed this were far enough away that they didn't have to worry about that. All right, so let's continue on. And again, let's pay close attention to this time down here. So 13 seconds, 14, 15, 16, and you can still see right around there. That's when it's about, the shockwave is just about to hit where the camera is. And there at 17 seconds. All right, so the explosion happened around 11 seconds, and then 17 seconds is when we heard the shock wave. All right, so if we apply a little bit of our math here, what we got is the following idea, is that we have, that again. So the amount of time was 6 seconds. Now we said 1 kilometer equals 3 seconds. So therefore, since 6 seconds have passed, we're assuming that it's about 25 degrees Celsius and it looks relatively warm. That implies that they're approximately 2 kilometers away from that blast, which is good because that is a safe distance to be. 2 kilometers is a fairly significant distance. I think the distance from well, let's actually take a look. Let's find out how far 2 kilometers is. So let's go up to Mama T. Here we go. And 2 kilometers from Mother Teresa is just past Fanshawe Park Road. So there you are, about 2 kilometers there. So that's the sort of distance we're looking at. So it's past the Home Depot, pretty much where the Starbucks is. That's the distance. That's 2 kilometers away. So that's how far away they were from that explosion, which is why it took that amount of time. So that's about, generally speaking, a fairly safe distance to be from an explosion of that size. So there we go. So you have some new information now. So now you can correct anyone when they ask you to use the 1 kilometer equals 1 second rule with thunder. You can correct everyone. You can be that insufferable physics person and say, well, actually, with your neck beard, and you can say it's actually 3 seconds equals 1 kilometer, which means that the storm is actually closer to you, which means that you're actually closer to death. So if you see the lightning and within a second you hear the thunder, that means it's under 347 meters away from you. If it's a fraction of a second, it's even closer. So just so you know, the storms are actually closer than you thought. So let's take a look a little bit further here. So again, sound is like any other wave. It can reflect off a surface. And when a sound reflects off a surface, we get what's basically a fixed end reflection. So we get sound cancellation at the wall. So we lose amplitude. So the wave stops at that point. It reflects back inverted. So this is why in your room you get some weird spots where the sound changes as you walk around in the room. For people who are into audio like myself, this can become a significant problem because in areas of destructive interference, we lose sound waves. So audio engineers painstakingly have to try to eliminate some of these reflections from causing problems with the sound. So that's why a lot of recording studios have foam and stuff on the walls, and movie theaters as well, to absorb some of the reflections, because you want the direct sound from the speaker and you want to minimize the amount of reflections, unless of course you are trying to get an ambient sound known as reverberation. And that's another thing where you go into certain buildings and you can hear your voice echoing along, which is a desirable effect for things like vocals, for drum kits, and all that sort of good stuff there. But that's information for a different lesson. So, standing waves and sound. How are they related and how are they beneficial? Well, as I just mentioned, in recording spaces, standing waves can be a problem. They can cause the room to sound weird, either remove bass, make things too trebly, or make them too mid-rangey. But standing waves are precisely how instruments actually operate. Every musical instrument requires a standing wave and resonance for them to actually produce a tone. So just like we talked about with the string, we have the different types of standing waves. So for example, let's talk about a sealed air column. Well, a sealed air column behaves just like a string fixed at both ends. So with a sealed air column, you get both odd and even harmonics. So we get the first, second, third, fourth, fifth, etc. So examples of this would be like a sealed drum. So drum kits have both skins at the bottom and skins at the top. So they behave like this type. So they produce a series of harmonics, and that's what gives the actual timbre or the quality of the tone. This is why different instruments sound different. They can play the same note, but the reason why they have a different tonal variety is because the amount of each of these harmonics that is part of the sound. So when an instrument is struck, it's producing all of these harmonics at the same time, but at different proportions to each other. And that's what makes a piano sound different than a bass guitar, which sounds different than an acoustic guitar, which sounds different than an electric guitar. It has to do with the relationship of all of these frequencies and how loud they are relative to each other and how quickly they die out. So sealed at both ends air column, a best example would be, your drum kit with a skin on the top and skin at the bottom. I also have a guitar amplifier cabinet. A sealed guitar cabinet also operates in this way. So like a classic Marshall cabinet, speaker cabinet is sealed. So we have the speaker here and it's closed back. So it's this type of resonance. Now, we also have a type of resonant air column where it's open one end, which means we have a node here and we have an antinode here. An example of that would be your clarinet or an oboe or saxophone, etc. All of these things where it's open at one end, and over here we technically, even though we have an opening here, we have a reed. This behaves like a node. So antinode and node. Now, what is interesting about these types of instruments is that they produce only the odd harmonics. So with these instruments, we go from the first harmonic to then the third harmonic. So there's a significant jump in frequency. So these ones only produce the odd harmonic series, which is why they have to be played slightly differently. And then an example of open both ends would be something like a flute, because we have an opening here as opposed to a reed. We actually have a physical opening, and to play a flute, you blow wind across the opening, right? You don't blow it directly in, you blow it across. That produces an antinode there. We have nodes, and then we have an antinode at the end. And of course, we have all the harmonic series happening. So they behave just the same way as the stringed instruments do. The same way as the resonances that we talked about earlier in the last note with waves in general, where you have open both ends, fixed one end, and open both ends. These are just practical musical applications to those theories. So next, we're going to talk about factors that affect the factors that affect frequency in guitar strings. So the next thing we're going to talk about is how guitar strings resonate and what factors affect that. So in a guitar string, they're affected by the following things: the length of the string, the tension, the diameter, and the density. Now this symbol here, it looks like a P, but it's actually the Greek letter rho. So let's take a look at how these relationships work. So the frequency is proportional to 1 over the length. Now notice it's a proportionality, it's not an equation. We can actually turn it into an equation by putting in some constant. The problem is we don't know what that constant is, and that constant depends on the materials that are used. So a lot of times when we solve these, we use the proportional reasoning to solve these things. So basically, the big idea is this. If frequency is directly proportional to the reciprocal of the length, what that means is if we double the length, we cut the frequency in half. And that makes sense because longer lengths equal lower frequencies. Now, tension. Frequency is directly proportional to the square root of the tension, which means in this case that the frequency change doesn't increase as much as the tension does. So if we double the tension, so if tension is equal to times 2, right, the frequency only increases by the square root of 2, which is 1.41, I should say, 2, whatever. So, and this is why it's a common mistake with people who are learning how to play guitar is they put too much tension on the string and break it, because you have to increase significant tension before the frequency changes. And that's why guitar strings have different diameters, and to compensate for that, because diameter, the frequency is indirectly proportional to the diameter of the string. So that means if you double the diameter, you cut the frequency in half, right? So if you double the diameter, you cut the frequency in half, which is why the lower bassier strings are thicker than the higher frequency strings, which are thinner. So the high strings are quite thin. That way you can have a reasonable amount of tension and get the appropriate frequency. So that's why stringed instruments have different gauges of strings, is to give you a consistent range of frequencies, a diverse range of frequencies, but with consistent tensions. That way some strings aren't super tense where other strings are super loose. So that's why they set them up so that they have different diameters, right? So that the tensions for the same tuning is roughly the same throughout. And that is also beneficial, that you don't damage the instrument, because if you have differential tensions at the top and the bottom, you can cause the neck to warp. So that's why it's also important to make sure that with your musical instrument, especially like a guitar, is that you're using a consistent set of strings across it. Now, of course, for any guitarists out there, you can get various gauges where sometimes the bottom strings are a little thicker, etc. So those instruments are designed to handle a certain variation in string thickness and whatnot, but not too much. And it also depends on the preference of the player. Some players like their strings to be a little bit looser. Some prefer them to be a little bit more tense. It all depends on your preference. And then, of course, the last relationship is the density. So the density of the material. So most electric guitar strings are made out of a nickel composite. And those have a particular property that are important for electric guitars, because nickel is also magnetic, and the electric guitar pickups respond to changes in magnetic field. So it's important to have a metal in the string that will actually generate a magnetic field. Whereas classical guitars are acoustic and they don't require such a thing. So a lot of classical guitars use nylon strings now. Nylon is less dense, which means that you can have thicker strings, but have a higher tuning. So various materials are used for different properties. Acoustic guitars, generally speaking, use metal strings, because the metal strings tend to be more bright, give you a little bit more treble than the nylon strings. And also you can put an electric pickup in an acoustic guitar, so you can make it an acoustic electric combination. All right, so how do these formulas work? All right, so basically this, we don't really know how to work too well with the proportioning. So what we do is we convert them into an equation. So here's how it works. If you want to turn this into an equation, you just put in a K for constant. Doesn't matter what the constant is, because we're going to use proportional reasoning to solve this. So if you're just dealing with length, the formula would be this. If you're just dealing with the tension, the formula would be this. Again, we don't know what K is, but that will come out in the proportioning. If we're just dealing with the diameter, changes in the diameter, it's going to be 1 over K times 1 over D. And if it's the density, it's K is equal to 1 over the square root of rho. But what happens if you change more than one parameter at a time? So let's say we're changing both the length and the tension. Well, what you basically do is you combine the two equations. And when you combine the two equations, this becomes K of square root of T over L. Do you see? I just basically combine them. So again, the K would be different, but it doesn't matter. It's going to cancel out. What if we combined these two equations? Well, if we combine those two equations, frequency would be equal to K 1 over, well, it's D and the square root of rho. And what if we combined all of them? What if all the parameters happened at once? Well, then that formula would become this. So there's our constant, and we have the square root of tension all over L D square root of rho. So let's do an example. So let's say a string is resonating at 440 hertz. Now that's a standard A. That's a standard A in music. It's resonating at 440 hertz. Determine the frequency, the new frequency, if A, let's say we double the length, B, double the tension, C, cut the length in half and quadruple the tension, and let's go crazy. With D, increase the length by 20%, increase the tension by 21%, decrease the diameter by 15%, and reduce the density to 64%. All right, so we got a lot of things going on here. Well, let's start off with our first one, part A. So with part A, its length is 2 times. So we start off with our default F0, and since we're only dealing with length, that's equal to K 1 over L, and that's equal to 440 hertz. So the frequency in part A is we double the length. So that's K 1 over 2L. What I'm going to do is I'm going to bring this 2 out front. So that becomes 1/2, because remember the 2 is in the denominator, and we get K is equal to 1 over L. And what you should remember from early on in the semester is we have that whole pretty blue box business. So I don't know what K is, I don't know what L is, but I do know the combination of all of these things is equal to 440. So this becomes 440 hertz, 220. Half 440 is 220 hertz. Cool. Let's do part B. And let's not be lazy and make that an actual straight line. Okay, part B, we double the tension. So tension times 2. All right. So again, we start off with our F0, and we use the appropriate equation, and that's going to be K is equal to the square root of the tension. So there's our tension formula. And we know that that is equal to 440 hertz. Now in part B, we doubled the tension. So that's going to be K square root 2T. Okay, so I'm going to take out the 2 out, so that becomes the square root of 2. So I'm taking a factor of the 2, but it's in a square root, so I got to bring that out front. And I got K square root of T. Doing our pretty blue box business, I replace K square root of T with 440, because K square root of T is equal to 440, and I get 622 hertz. Easy peasy lemon squeezy. All right, next, part C. So we cut the length in half and quadruple the tension. So length is cut in half, and the tension now is 4 times larger. So what is that going to look like? Well, now our formula has to include both the length and the tension. So this is one of our combined formulas. So when we look, it's reciprocal to 1 over length and the square root of tension. So our new formula is going to look like this. K is equal to the square root of the tension over L, except one small little problem. That should say F0. And that is originally going to be 440 hertz. Now let's take a look at FC. Now we can do FC. So that's going to be 4 times the tension, and the length is 1/2. So that's going to be 0.5 L. So now what I do is I factor out the square root of 4, 0.5. Now notice this is in the numerator, this is in the denominator. So that has to stay in the denominator, and that has to stay in the numerator. So we've got K square root of T over L. Let's do some pretty blue box action, except on the right spot. All right. So that's going to be 2 over 0.5 times 440. It's 4 times 440, 1,760 hertz. And that's quite a high frequency. One could say that it actually hurts. No? All right. And let's take a look at part D. So with part D, length. Length increases by 20%. So when we increase by 20%, that means the length is now 120. Length is now 120%, which is equal to 1.21. Now, the tension increases by 121%. So our tension increases by 21%. So that means that's 121% or 1.21. What did I do up here? I was looking at the wrong thing. Sorry. The length increases by 120%. So that's 1.20 times L. Tension increases by 21%. So as a decimal, that's 1.21 times T. All right, now we're on the right track here. Okay, so next, let's take a look. The next thing is the diameter. Decrease the diameter by 15%. Okay, so now here's the important thing. If we decrease by 15%, that means there's 85% left because it says decreased by, and that's the key thing. When you decrease by versus decreased to, see that's a to, this is a by. So when we decrease by 15%, that means we take 15% away, which means 85% is left. So the diameter is now 85% of the original, which is equal to 0.85 times D. And then the last thing is the density is reduced to 64%. So rho is reduced to this value of 64%, which is 0.64 times rho. All right, so now in this version, we have the combined formula. So the combined formula is going to be F naught. Naught stands for original. K, square root of tension, and we've got length, diameter, and the density. We know that all equals to 440 hertz. So now the frequency of part D, so subscript D, is equal to K, square root of the tension, which is 1.21 times T, over the length, which is 1.2 L. I'm going to put that in brackets to keep it a little cleaner. 0.85 times the diameter, and the square root of 0.64 times the density. Now, let's just clean that up a little bit better there. Okay, so now next step is we got to common factor out these numerical coefficients. So since this is under the square root and it's in the numerator, square root of 1.21 like this. This is in the denominator, so it all has to stay in the denominator. So that 1.2 in the denominator, 0.85 stays in the denominator. And the square root, we should clean that up a little bit there, all has to stay in the denominator. And then that becomes K, square root of T, L, D, square root of rho. All right. And again, our little pretty blue box. So we can replace this K square root tension LD over LD square root of rho with our 440. And we get 593.1 hertz. And that's how we do factors that affect a guitar string. So next, we're going to talk about the intensity of sound. So when we talk about intensity, most people think of the volume, how loud something is. All right. So how loud something is actually a psychoacoustic experience. So what we perceive as volume is how our brain interprets the intensity of a wave. So what is the intensity of a wave? Well, it is a relationship between the power of the sound source, so how much energy over time it delivers, as well as the distance that we are away. So if you recall in the shockwave video, and let's go back for a moment, if you watch carefully, when we get to the 11-second mark, now, if you look, you can see that the shockwave is a circular disc. But actually, what you don't see entirely is that it's not actually a disc, it's actually a sphere, right? It's a big shell, because the shockwave is also happening up here as well. So it's a big growing bubble. And if we pan out, let's see if we can actually see it a bit more. Yeah, so you can see the shockwave moving this way. And there are other videos that show the shockwave in high detail. So we're going to mute the brutal music here. So here's an example where you can really see, and there it is right there. You can really see the shockwave, and if you follow there, you can see the shockwave growing like a half sphere. Now, the reason why it's a half sphere is because obviously the ground is blocking it. If it was actually in the atmosphere, it would be a perfect sphere. So you can see the shockwave growing out. Now, sound is a much less intense wave being generated, but its behavior is can be described in the same fashion. So if here is your sound source, the energy of that wave is moving out away from the center along these radial lines. And if you imagine this is just a slice of that sphere or that shell, the energy of that sound wave is going to be distributed across the surface of the shell. So when we talk about the intensity of this wave, it's based on the power divided by the area of this shell. Well, the surface area of a shell is the same as the surface area of a sphere, and that's equal to 4 pi r squared. And this r squared is very important because the intensity decreases to the square of the distance that we are away from the source. So if you double the distance you are away from the source, you actually cut the intensity by 4. If you're 10 times further away, you increase the intensity by a factor of 100. So distance has a very important relationship to how loud or how intense the sound signal is. So it's based on the inverse square law. So our first formula for sound intensity is the power of our source divided by the area of the surface area of this sound shell, which is 4 pi r squared, and that's measured in watts per meter squared. So sound intensity is equal to power over 4 pi r squared. That's one way of measuring intensity. But the interesting thing about the human ear is we hear things in a non-linear fashion. The human ear has an incredible range of sounds that we can hear, from extremely quiet to extremely loud. So the decibel system was invented. Now, the person who invented the decibel system is Alexander Graham Bell, which explains why the unit looks like this. Now, Alexander Graham Bell actually used just bells. We've modified it to 1/10 of a bell. That's where the D comes in. The little d stands for deci, which is tenths, and capital B stands for Alexander Graham Bell. But the spelling has been changed to decibel like this. But really, it was 1/10 of a large bell, hence Bell telephone. So that's why this unit it's spelled differently, but that's just because they changed the spelling. But really, that's the way it should have been, is like this. All right, so now the formula for sound intensity in terms of decibels is a little bit weird. So we have the Greek letter beta, which stands for the intensity in decibels, is equal to 10 log I2 over I1. All right, so this is using a little bit of math that you're going to be more familiar with in grade 12, but something called a logarithm. And I'm just going to quickly explain what a logarithm is. All right, so for example, if you pause the video and grab your calculator, we're going to do a little experiment here. So what I want you to do is I want you to look for a button on your calculator that says log. It may say log 10, but specifically most of them just say log. But I'd like to see if you have multiple buttons, it's log 10 that we want. All right. So the experiment is this, is I want you to type in log button and then do the log of 10. And when you do that, you should get an answer of 1. Then do log of 100. You should get an answer of 2. Log of 1,000. I think you can see a pattern here. Log of 10,000, and we get 4. So what is this log business? Well, what this actually is what log tells us is the following. And this translated is really this. What exponent of 10 gives us our value x? So this is just another way of writing this right here to the right. All right. So if we take a look, 10 to the exponent 1, 10 to the exponent 1 gives us 10. 10 squared gives us 100. 10 cubed gives us 1,000. 10 to the 4th gives us 10,000. So this is just another way of writing a power expression, or exponents if you prefer. So to solve questions that involve the decibel, we need to know the ratio of two different intensities. Well, the problem is we don't always have two intensities here. So we're going to talk about the lowest intensity. Note, the quietest sound, actually, I should probably type this up. The quietest sound the average human ear can detect is 1 times 10 to the negative 12 watts per meter squared. So where did this number come from? Through testing. So basically, audiologists over decades have tested literally thousands upon thousands of individuals with undamaged hearing, of course, and that's usually the young. and they take an average of the quietest sound that we can hear. So basically, they put you in a booth with a pair of headphones on, and they play little sounds through those headphones, and you are to indicate with your hand whether you can hear a tone or not. And it works out that on average, the undamaged human ear can hear a sound at about this intensity, which is 1 times 10 to the negative 12. And that's a very small amount. Remember, a billionth is times 10 to the negative 9. So this is a trillionth of a watt. So this is the sound of like leaves rustling under a gentle wind in a forest. We're talking that level of quiet. So we can hear that as the quietest sound that we can detect. So the ear is actually quite sensitive, and this is the average. Some people can hear better than this. Some people can hear worse than this. As you get older, your sensitivity becomes much less than this, and some people can actually hear below this value. Other species, for example, dogs, anyone who owns a dog knows that dogs can hear extremely well, where you and I will not notice anything, and a dog will hear somebody walking down the street from a block away and start going crazy and barking at them. So this is also species dependent. So this is an average amount for most people. So how do we use this in the context of this formula? Well, let's do an example. A guitar amp, actually let's put a 100-watt guitar amp, is blaring away. We want to determine the intensity of the sound in both watts per meter squared and in decibels if the sound source is 1 meter away, 2 meters away, 10 meters away. All right, let's get into it. So, part A. Intensity is equal to the power over 4 pi r squared. So that's 100 divided by 4 pi times 1 squared, and that's 7.95 watts per meter squared. Now in decibels, beta is equal to 10 log. Well, in this case, it's going to be I over I naught, where our I naught is equal to that 1 times 10 to the negative 12 watts per meter squared. Because we have to compare two intensities, and we're going to compare it to the lowest that we can hear. So 7.95 divided by 1 times 10 to the negative 12, and that's 129 decibels. That is extremely loud. That is the equivalent of standing next to a jet engine. So having a guitar amp at that volume, at 100 watts of sound power, blasting your head, is actually quite dangerous to your hearing. This is guaranteed hearing damage. So let's do part B. So let's find the intensity when we're 2 meters away. So that's 1.99 watts per meter squared. Let's calculate the decibels. So 10 log 1.99 divided by 1 times 10 to the negative 12, 123 decibels. And that would be the sound of an extremely loud concert. And finally, part C, when we're 10 meters away, realize I made a small mistake over here. That should be a 6. So 0.0796 watts per meter squared. Now, if we're 10 times away, that should be a decrease by a factor of 100 because of the inverse square law. And that works out to 109 decibels. All right, so let's take a look at the three numbers that we got in terms of the decibels. So we first had 129 dB, and then it went down to 123 decibels, then down to 109 decibels. So let's look at this in terms of decibel loss. This is minus 6 dB, and here, from the original, that's minus 20 decibels. So here's an interesting thing. 3 decibels equals 2 times, or a half power. So that means with 6 decibels, that's 2 times 2, or a half times half, or a quarter. And if you recall, I said it's the inverse square law. So since we doubled the distance, double squared, that's equal to 1/4 of the intensity. So this is 1/4. So 6 decibels is doubling up this half loss. So a half and a half equals a quarter. That's where we get the 6 dB from. Now, 10 decibels equals 10 times. So a 10 decibel increase is equal to 10 times louder, or cut by a tenth. So 20 decibels is 10 decibels and 10 decibels. So that is going to be 10 times 10, or 100 times, or a tenth times a tenth, which is 100th, which makes sense because this is 100 times quieter, because 1 over 10 squared is 100th. So that's how you can actually do a quick little conversion by just looking at these decibel numbers. Very handy if you're a recording engineer. For a regular person, not so much. But in any case, so that's sound intensity. So the last thing I want to talk about is beat frequency. Okay, so for this demonstration, I have my recording software up here. So I'm setting up two tones, both operating at 100 hertz. Let's take a look here. So our sound number 1, which is represented by this channel right here, we're producing a 100 hertz tone, and sound number 2, which is represented by this channel over here, is also operating at 100 hertz. And over here, we have an oscilloscope. So when I turn on one of the channels, you can see a sine wave and you can hear that sound. I'll mute this channel and I'll turn on the other channel. And as you can hear, they're identical. Now, when I turn them both on at the same time, notice that the amplitude increases when I turn them on. And the reason why that is we're getting constructive interference. Now, the next thing I want to do is I want to change the frequency of one of these to 101. Now, what you should be able to hear is that the volume is going louder, quieter, etc. Well, why is this occurring? Well, what I'm going to do is I'm going to take the waves and I'm going to separate them. So right now they're both coming up the middle. So they're interfering with each other. Now, when the sound is loud, we're experiencing constructive interference. And when it's quieter, we're experiencing destructive interference. So now I've moved them to left and right. So you're not going to hear the interference, especially if you're listening on a pair of headphones. If you're listening on your stereo with a Bluetooth speaker, you might be able to hear it. But you can see how one of the waves is moving, the other one appears to be stationary. And as it's flowing, you're seeing that the waves line up sometimes and other times they do not. Let me put them back in the middle again. Now what I'm going to do is I'm going to change the frequency difference to 100.1. Now it should happen a little bit slower. Loud, and then you can hear the volume cut out, and then it goes loud again. So now I'm going to put them back in the left and right channel. And what you're seeing here is that what's actually happening is when the waves line up with each other, we get constructive interference, and then it goes to destructive. Now I can do this, actually, I can cheat. There we go. So now you can hear it going from constructive interference to destructive interference. Constructive, then destructive. And this oscillation that you hear is what we call the beat frequency. Now, if I put it up to 102, and if you get a stopwatch, it would be 1 2 1 2 2 beats per second. And how do I get that number? How do I get that 2 beats every second? That frequency is 102. This frequency is 100. The difference is 2. So that means this interference pattern of loud, quiet, loud, quiet, loud, quiet is happening 2 times per second. Now, if I change it to 103, 1 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3. We basically get a waltz. So we get a difference of 3 hertz, so the beat frequency is 3. Now, here's the interesting thing. Put it back to 100. So back to 100, they operate just normally. But what if instead I go lower? Doesn't make a difference. The beat frequency, all it matters is the difference in those two. That's it. So if I go back down to 97, we still have that 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3. Now here's some fun stuff we can do with this. This, incidentally, is how musicians often will tune their instrument. Because if they hear this beat sound, they know that the instrument is out of tune. All right, so now I gotta get my wave started. There we go, back in phase again. Okay, now applications of this. Beat frequency is actually part of what makes music music. So what I'm going to do here is I'm going to change this to a, well, maybe the square wave is a little harsh. I'll just turn the volume down a little bit. Now I'm going to make some Nintendo sounds here. Second. Turn this volume down a little bit. Now I'm going to change the frequency. 101. All right, so there, you get some classic video game sounds there. All right, so some of the sound effects from old video games use basically tone generators like I'm doing right here. But here's the next thing. Check out the mathematical relationship. I'm now going to change it to 125. Now 133. Oops. $150. 166. 175. 200. So in fact, what I did is I basically just created a harmonic series, basically the notes in our musical scale. So music is actually just a mathematical relationship on frequencies. So here, when I have double the frequency, I'll put it a little off there so we get that little chorusing effect. This is considered a whole octave. So we are double the frequency, that's a full octave. Now if I do 1/4 of the frequency, so 125. So that is a 1/4 increase, that's a whole note. Now I can cut this quarter in half and I get 112. And then down to 100 again. Let's do 101. On 12.5. So this is your do, re, mi kind of thing going on here. $166. And there's your entire scale based on the beat frequency, which I think is pretty cool. All right. So let's get back to the original note there. Put those down. So the formula for a beat frequency is just the absolute value of the difference of the two frequencies. So this is how you can actually play two notes and get a third note generated between those. And that's why when you have an ensemble of instruments, a handful of instruments can sound like way more. And that has to do with the fact that when two notes are sounded together, you get a third one in between them, which is equal to their difference. And so that's the concept of the beat frequency. So it's just the absolute value of the difference between the two. So an example, so let's say we have one note, our F1 is equal to 440, and our second frequency is equal to 397 hertz. So the beat frequency is just equal to the absolute value of the difference between the two. So it doesn't matter which way you subtract, I should say. You're just going to take the positive value anyway, and 3 hertz. So the interference that you would hear would be varying 3 times per second. And that's it.